Okay, so actually I thought I'd talk about three results, and I guess one common theme is their results that were first done a long time ago, but now they're new arguments to a large extent, certainly with my own result, much better arguments, and also with different aspects. And the first two results have an algorithmic aspect, which is very important. So the first one, I'm bringing Coles to Newcastle and talking about the recent result of Shekhar Lovett and Raghu Meka and Oded Regev. On my own result, sometimes the title of the paper was six standard deviations suffice, and somehow that title stuck. And so that was back a few years ago. It was actually done in 1984. I was at a conference in Vienna on number theory, and I had the very good fortune to go to a very boring talk. And while I was at the talk, I started thinking about the problem. And by the end of the talk, it's just like in the movies, like, you know how in A Beautiful Mind, how they, suddenly Nash sees the answer? Well, once in my lifetime it did happen, and by the end of the talk I had the result. But now it's much better.
So you recommend number theory?
I recommend going to boring talks, yes, very, very much so. And the other one is by Robin Moser. Now it's a couple of years ago, so Robin was actually, I think, a second-year graduate student when he discovered this. And then Gabor Tardos came in and got another viewpoint, and a lot of other people, including my own postdoc, Wes Pegden, who was Beck's student. So other people have worked on it. And this is a new approach to the Lovász-Local lemma, which Lotze had in '75. Another interesting story about that, I heard about this result. Maybe you don't know this story, because I heard about the result. At that time, communication between the United States and Hungary was not so good. I mean, it was the middle of the Cold War, It was like North Korea and South Korea, You really couldn't just send letters. But I did get a letter from János Komlós. And he wrote, and he said, here's this new result by this great young guy named László Lovász. And that was the first time I heard about it. And he gave the proof, and indeed it was there. So I'll talk about that. And then the third one, the result is by Sumik Pal, excuse my poor pronunciation of Indian names, who's a junior faculty at, assistant professor, I believe, at University of Washington. And the topic here, C of nk, is the number of connected graphs on n vertices with n minus 1 plus k edges. So k equals 0 is trees, is the classic result of Cayley. And this goes back to for k fixed, it was done by E.M. Wright in 1977. And then the general result was done by Ed Bender and Rod Canfield and Brendan McKay in one of the first issues, I think it was the first issue of the second volume of Random Structures and Algorithms, and we were so happy to get that result. And now Sumik has a new approach to it for some ranges of k, as I'll explain later. So if there's a general theme, one of the general themes is new and better approaches to old results. So I want to start by stealing your thunder and giving you my take on your result. Now, actually, I should say all I have on your result is that Nikhil Bansal sent me an email and gave a rough description. So I hope it's correct. Me too. I know your result is correct. I hope that the way I presented it is correct. Okay, so first let me state my result in a somewhat different way than usual, but it will help. So we have some vectors. We have n vectors in n space, and all of the coordinates are at most 1. The L infinity norm is at most 1. And then the claim is that there exists a plus minus 1 vector such that if you take its dot so that it's you might say nearly orthogonal or close to orthogonal. Well, anyway, here it is, that the dot products in absolute value are less than or equal to 6 squared of n. And the crucial thing is for all of the n vectors, not just 99.99%, which would be easy. We can get 99.99% by taking a random plus minus 1 vector, and then the dot product will be a Gaussian with standard deviation root n. So the chance of being 6 standard deviations off the mean is like, I don't know, 1 in a million or something like that. But we want it for everything. So, and if you do that argument, you can do it with an extra polylog term, but we want it without the polylog term. It's crucial. So the whole thing is saving a polylog term. Okay, so here is the new result. I shouldn't say et al. When you're in the audience. So. And let me state it in a way. Now, one of the ideas here is we want to get a vector which is plus 1, minus 1. And we think of this as a coloring. In fact, the initial problem was due to, well, who else but Erdős. And you had n sets on n elements, and you wanted a coloring. And the coloring you could think of as a plus minus 1 vector. And each set you could think of as a 0, 1 vector of the incidence in it. And then you wanted a coloring so that all the discrepancies were small. But I'm going to move away from that and look at it in this vector format. Now, one of the ideas is you want this x to be, all the coordinates to be minus 1, plus 1. And there's this idea of floating colors. So what's going to happen is as the process is moving along, the colors are going to move around between minus 1 and plus 1. They never go over minus 1. They all start at 0. There's the values of the vector x. It starts at the 0 vector. It's going to move around, and at the end, all the coordinates will be plus 1, minus 1, and we call that the floating color idea, which has probably, it's hard to say. I like to attribute it to Beck. You know, it's such a natural idea, but he certainly made use of it very early on. So let me state the thing. Instead of starting at 0, we're going to have some initial vector, and we're going to have m coordinates, and we'll see later how this fits in. And now we're going to have some vectors of Euclidean norm less than or equal, or let me write it this way. The vectors are in Rm, and they're going to be n of them. And their Euclidean norm is going to be less than or equal to 1. And I'm going to think of n as being bigger than m. And in fact, I'm going to just parameterize n to be m times 2 to the k. And actually, the case k equals 0 is important. But to get the full result, we do it for each k. And, well, we want to get the xi's to move to the boundary, to plus or minus 1. But since this is a discrete process, we're not going to move them exactly to the boundary, at least not in this argument for it. And so we'll just move it near the boundary, and then at the end, if it's close enough to the boundary, we just round it off to the boundary. So if we make it within 1 over n of the boundary, it's not going to affect this when we round it off, because when we apply it to this result, it won't matter. So we'll call xi borderline.
I has nothing to do with the other I.
That's right. Call xj borderline if its absolute value is greater than or equal to 1 minus 1 over n. The idea being we'll just stop then, because then the round off, because in the end we're only going to have vectors of length n, so the round off isn't going to have a effect. I mean, this could be improved, but we'll just call it borderline there. And now what we're going to do is we're going to move in steps x initial to x. So the sort of the picture is, here's our x initial. It doesn't have to be at the origin, but you might think of it at the origin. But when we wind up in the end using this in the induction, it's somewhere. And we're going to move it around. So it's going to sort of float around. And what's going to happen is, and now as we're moving it, so we think of x at various times, x is sort of moving around. And the ith error is the dot product of how far we moved with our, so if you like, think of x initial as the zero vector. I mean, if you've just seen this for the first time, just think of it as, I'll put the absolute, let me just write it this way. Yeah, I want to write it without the absolute value because it's going to have a Brownian motion to it. And what we're going to do, the claim is that we're going to be able to do this so that m over 2 coordinates are borderline, that is at the end of the process. And we'll stop the process when half of the coordinates become borderline. And the crucial thing is that all of the, now it's the absolute values of the errors are at most some absolute constant. So C is like 3 or something. It's an absolute constant times square root of m. And then an additional factor of square root of n, of square root of k. I guess when k equals 0, it's not square root of 0, but yeah. So it's some number. Okay. So what we're doing here is, all right, now let me jump to the end and see how you put this, given this result, how you get this result, because it's just in stages. You start with an x in n dimension. You start at 0, so none of the coordinates are borderline. And then in phase 1, you're moving around until half of the coordinates become borderline. And then in phase 2, you move around until 3/4 of them become borderline. In phase 3, until 7/8 of them become borderline, etc. Now, what this says, now, because the original R's had all coordinates at most 1, when you have n times 2 to the minus k, once a coordinate becomes borderline, you don't touch it anymore. So if you're down to, say, n over 8 coordinates that are non-borderline, you're now in n over 8 space. So m space, m is n over 8. And now you're going to use this, you're going to move along until half of those coordinates become borderline. So you start with n over 8 coordinates, but you still have n vectors. You still have n vectors, that's important. You have n over 8 coordinates, and you move them around until half of them become borderline. And that stops this phase. So if we have this result, in phase 1, we move it so that all of the errors are at most this absolute constant times square root of n times, say, 1. It's not square root of 0, it's 1. But then the second time we do it, that is to go from n over 2 coordinates borderline to n over 4 coordinates borderline, this m is now n over 2. So we gained a factor of square root of 2, and we lost a factor of square root of k. But notice this is a logarithmic factor in n over m. So if m, you can't see it at k equals 2, but when k equals 50, when you have n times 2 to the minus 50 things, in that phase, you're gaining 2 to the minus 25 here, and you're losing a factor of square root of 50. So what happens is the infinite sum converges, and you wind up that the total error. So this is the algorithm is in phases. Phase 1 until half of them are borderline. Phase 2 until, let's say, a quarter of them are not borderline. Phase 3 until an eighth of them are not borderline. And in each phase, it's like it's the square root. The errors that you get are like the square root, except that there's this extra factor, but it's negligible compared to this. So if it was only the square root, you'd have a geometric series summing the errors, but it's still a convergence series, and that's it. All right. So this is actually what one is going to show, and indeed, think of m equals n because that's the basic idea, anyway.
So you just switch from the L infinity norm to that.
Yes,
norm.
just at this point. Yeah. Oh, I'm sorry. Thank you. Good point. Right. Now, interestingly, here to show this result, we might as well. We actually could consider them as unit vectors. The square root of m doesn't come in. So when we state this, dividing by square root of m. So we can think of this result as saying that you have n unit vectors in the Euclidean norm, and this becomes a constant. This goes away, and this is like a square root is a square root of k term, a square root of k term. So you can certainly think of it that way, but I'd rather leave it in this form. But thank you for the correction. All right, now let me give the idea of it. How you're going to move x around. You're going to move x around with Brownian motion, except it's a restricted Brownian motion. Once a coordinate becomes borderline, it's frozen, and you're not allowed to change that coordinate. But the key thing, as I see it, is this. Let me back up. The whole problem is outliers. This is really a problem about outliers because most of the dot products are going to be pretty good because you've got some kind of Gaussian tail. Again, think of m equals n for the rest of the talk. It's just, so, I mean, most of the time you're not going to be with outside of 6 root n, but you're going to get some outliers. And the key thing is this. As you're moving around, you look at these errors without the... So you look at these errors, and if the errors start to get big, in fact, the way I'm going to show it, I'm just going to take the top few errors, and I'm going to freeze those errors. So let me show you how I do it, or not me, it's them, how they do it. Okay. So what I want to do is to move in a small step. I mean, I think of it as Brownian motion, but it's really, it's a discrete algorithm in this way. And here's the restriction on y. Sorry, yi. This is going to be the movement the first one, once an xi gets to the border, we just freeze it. But then the second one is the key. We're going to make it orthogonal to Ri for, let us say, the m over 4 i's with the biggest current errors. Current errors. So the error is changing in time. And we restart the phase. So here we're just doing, and again, just think of m equals n. We're just floating around. And so m equals n, and when something reaches the border, we freeze it, but we're going to stop this whole phase when half of them reach the border. So at most m over 2, that's at most m over 2 conditions. And at any time, and which ones these are going to change, and this is the absolutely critical thing, we're going to take the RIs that are the most dangerous, if you like, the m over 4 of them that are the most dangerous, and we're going to insist that those errors not change by insisting that where we move is orthogonal to the RI. Our movement, our delta x, is going to be orthogonal. Now that's a total of at most 3m over 4 conditions, so we still have a lot of space. So what happens is let V be the so these conditions here give a linear, they're both linear conditions, and they give a space V. And the dimension of V, we haven't lost too much. I mean, constant factors are all right. We're not too. So V, in our restriction, instead of doing our Brownian motion in dimension m, we're doing it in dimension m over 4. Now, what do I mean by Brownian motion? Because we make this a discrete discrete space. Yeah.
M over 4 or 3m over 4? Is it m over 4 or 3m? Yeah, that's what they meant.
No, after V is. Oh, V is what's allowed. These are the restrictions. Sorry.
So it's m over 4 dimensions that are lost because of the restrictions, and m over 2 might be lost because of the borderline element.
Exactly. That's exactly.
The beginning is 3m over 4, but at the end it's only m over 4.
Yeah, there's at least m over 4. Yeah. Right. So we still have. So V is what's allowable, not what's restricted. The orthogonal space. So we've still got a lot of space. And now, when I say Brownian motion, let's just put a Gaussian on V. So we put a Gaussian distribution on V, and I'm just going to normalize it in this way. That is, if V has dimension S, you just take an orthonormal basis, and then each coordinate is standard Gaussian, but then you divide by square root of S. So there's just a standard Gaussian. And now, so I just want to have some normalization here, so I'll just take that one. And what happens, so this is our randomness, is in the choice of the Gaussian, the point from the Gaussian distribution. And now let's look at R dot n. This is also Gaussian. With sigma less than or equal to square root of m, because I made the square root of m instead of 1. Actually, now it's handy to make it square root of m. Divided by, because the square root of m, now it's a unit vector. And nice thing about Gaussians is that they're direction independent. So I always you don't have to recalculate. Just think of R as being 1 and all zeros. And so R dot n is just the first coordinate, which is Gaussian with standard deviation 1 over the square root of the dimension. So this is square root of m over 4. And the 4 doesn't hurt us very much. It's Gaussian with standard deviation at most 2. So that what's going to happen is that this restriction, I mean, if we really look at the constants, we'd want to tighten it up. And the m over 4 doesn't have to be m over 4. And the phases could be defined differently, but this will be enough for us. So now, what we do is the movement is going to be some small epsilon times this random normal. Now, as epsilon goes to 0, we're approaching, it's like a Brownian motion, except it's a Brownian motion where the space in which you have the Brownian motion keeps changing as the EIs start varying. And think of epsilon as n to the minus 5, but some really small number in terms of the algorithm. But actually, we want to make it, for the effectiveness of the algorithm, we'd like to make epsilon as big as possible, and that's an interesting problem. But I think of this as kind of a continuous process, and this is just the discretization. So now we move our ith step, or tth step, is, oops, yeah, well, I think I can write it this way. Yeah. All right. So what is the general step? We're at some value of x. We have these linear conditions that create a subspace of dimension at most n over m over 4, at least m over 4, at least m over 4. And then we take a standard Gaussian, given those conditions, and then we multiply it by a small number and just add it. One of the things about the small number is the choice of how small epsilon can be depends on the notion of borderline, because we never want the x's to jump over the border. So again, there's some technical stuff in making the algorithm a lot quicker. The thicker the borderline, the bigger you can make epsilon. So this is an issue. But I'll just think of epsilon as n to the minus 4 for now. Okay. So now what happens, as a continuous process, it's Brownian motion, but in this seminar, would like to have a discrete algorithm for it. So here it is. So what's going on here is that when we add to x epsilon times the standard normal, the square goes up by roughly epsilon squared. Actually, I've had some email with Shakar about this. Pedagogically, what I prefer to add in a condition that y be orthogonal to the original place. It just, because then you're more sure of this. Turns out you don't need it, but it's the way I think of it. Anyway, so
That's an expectation.
this is an expectation, but like I say, if I just added a condition 3 that y was orthogonal to x, which is only one condition, then this would be not only an expectation, but very, it would simply be what is the norm of n, and it's high dimensional, so it's very highly concentrated. So yeah, it's an expectation, but there's a high concentration here. And it turns out you don't have to do that, but I'm going to put it in anyway, because I like it. It's only one condition, because it just helps with the working here to make sure that you're what's happening. So therefore, the number of steps, so now let's say that there are t steps, and I claim that t is less than or equal to 4m to the 1/2 epsilon to the minus 2. You'll recognize the epsilon to the minus 2 is just the scaling factor. Why is that? Because we're starting somewhere inside the unit cube, and we're ending up inside the unit cube. By unit cube, I mean from -1 to +1, not 0, 1. So the total distance we traveled was at most 2 squared of m, so the total distance squared is 2 squared of m. And I forget why the 4 is here. We're increasing the square. We're going by epsilon squared. So the norm squared is going from at least 0 to at most, at most 2. Yeah, there's somehow I'm missing a 1/2.
There's no
I just think x is. Yeah, okay. That's good.
The exponent I don't see, m to the 1/2.
Oh, wait, maybe that's right, wait. Maybe I missed. You're going m. It should be m, okay. It's going to work. Let's make it m, okay. That's right, because the final one has norm, has norm square root of it. Think of x as the origin at the beginning. The final x has Euclidean norm square root of m, so the square is m. Yeah, okay. Okay, and the extra factor is just because you might be starting way near one corner and end up in the other corner, so you've got a constant. Hopefully this doesn't knock out the proof, but okay. And now what's happening to the EIs? Well, the EIs are bounded to each error. Now, this is why I took off the absolute value signs. I mean, the error is moving by a normal, and the sigma of the normal is bounded by 2 times, is bounded by 2. And so the sigma is like 2 epsilon. Actually, it's a martingale because that's an upper, think of it as a martingale. If you look at how the EIs are moving, they're like a martingale, and at each stage, there's a Gaussian move, including with sigma 0 if it's frozen. So it's making a Gaussian move, and it's bounded by 2 epsilon as its standard deviation. So if we did this to the end, we would say, for a particular I, what is the probability that EI final is greater than or equal to So what you're going to, because if this was because of the martingale, because of Azuma's inequalities, you have a tail distribution on the EIs, and this is going down by e to the minus alpha squared over 2. Now, that by itself, you'd again get the polylog term because you want all of them to be small. But here's the key thing. We're going to set alpha so that this is less than 1 over. So here alpha is like constant square root of k. So alpha is going to infinity, but at this low rate. Now what happens is that the expectation of the number of I that end up being outliers. So this is we're going to want that all of them are less than or equal to this. So the expected number, oh, even one thing more, because it's a martingale, not only EI final, but you could actually say at any particular time. So I can actually say from this the probability that the max over time of EI is greater than Cm to the 1/2 alpha is less than.
It's martingale until it stops, right? Well, it behaves as martingale until you apply condition 2, right? I mean, it's not martingale forever.
It is a martingale when you apply, which is condition 2.
When somebody reaches a border, you fix it.
That's okay. The EIs are still going by a martingale. If they're frozen, it's a martingale where they're not moving. So it's still a martingale. It's still okay, yeah. So not only the final one, but just a nice technical point. Even in the middle, you could, since this is a martingale, you could say, look at the maximum you ever achieve. And again, the same as this again You could apply a martingale inequality and say it's less than this. So what's saying So what's happening is when you apply this process, the expected number of outliers, so an outlier is if it gets bigger than this, and the expected number of outliers is less than m over 4. I mean, we set up alpha to make it less than m over 4. But now, this is the whole point of doing the freezing. We always froze the top m over 4. So we have this process. And we know, so let me use Erdős magic. There's some running of this process so that only no more than m over 4 of them ever become outliers. But that means that none of them ever become outliers because the top m over 4 are always frozen. So this is the key thing. You avoid the outliers by freezing the top m over 4. So the way I think of it is you've got these n different Brownian motions, and they're all you have to use expectation because you have no hold on how they're on their lack of independence. Let me just finish. So you have these n different random walks, but at any time you take the m over 4 of them that are the biggest and you freeze them. Yeah, Russell.
So we could do it the other way.
Yeah.
Which is to say, when it reaches Tm to the 1/2 alpha, then we freeze it and argue that because it's a martingale, so then it's a martingale throughout its life.
Actually, that's
and then we just argue that they're most over 4 out.
So let me just repeat that for those that didn't catch it. Maybe even a better way to look at it is instead of freezing the top m over 4, only freeze it when it reaches here. And now you say that only a quarter of them are going to be frozen, and then you go back and you get this. And so this is the result. It's when you look at the algorithm, what are the steps of the algorithm? You've got to find an orthonormal. Graham-Schmidt was what it was called when I was in college. I don't know. You have to find the orthonormal basis, and then you have to have a lot of randomness to get the normal distributions and things. But then you move around. So I haven't really gone into the quickness of the algorithm. But let me mention one thing about the quickness of the algorithm, and this I did write to Shakar about. One of the things that's helpful is that you can make the border actually very big. If you make the border 1 over poly, for the original problem, if you make the border 1 over polylog, let's say 1 over log n or something like that, then, and making the border really thick allows us to make the steps really big, because the restriction on the steps is that you don't want to jump over the border. And why can you make the border that thick? Because then, after you've reached the border, then you do a randomized round off. And then you can use standard Erdős magic and do some calculations. And when you round off and all of the numbers are within 1 over polylog of n of 1 or minus 1, and then by randomized round off, I mean, you round off keeping the expectation the same. And one can show by elementary methods that works. So actually, that's important in terms of efficiency because it allows the epsilon to be much, much bigger. But to me, the key idea is that we're worried about outliers, and so we handle the outliers. They handle the outliers, as I see it, by freezing them and just saying, as something is getting bigger, or as Russell would say, when it reaches the dangerous point, then you just freeze it. That becomes a linear condition, and you're not doing that often, so it's having some effect on the constants, but not very much. So some historical background. The original proof is very well worth not reading because, I mean, so many better approaches have been done. But then after the original proof, a number of people, especially Ravi Bopanna, came in and gave a proof involving entropy that was very nice, and that's the proof that's in my book with Noga that we use. But it looked as though there was a basic pigeonhole argument that was going on that made it non-algorithmic. And then about 3-4 years ago, Nikhil Bansal came up with an algorithm, but he used our result. Because he used semi-definite programming, and he created a problem, so I'm not going to give his result method also, but the basic idea was there was a semi-definite program. Well, it had a solution in one space because of my result. There was a coloring. There were these values, +1, -1. Therefore, the semi-definite, the relaxation, the vector relaxation was feasible and could be found via semi-definite programming. And then he took the solution to the semi-definite program and he used a random projection a la Gomans and Williamson. But I always like to emphasize it's not just a corollary of the Gomans-Williamson. It really has other ideas to it. So Bansal's result was great, and now this result is great. But yeah, I used to think, so one anecdote, and then do we usually take breaks in these things? Okay, yes, I think. So let me end this portion with an anecdote, which is, you know, I used to think that I'd get to a certain age, and so let me back up. So for a long time I conjectured, in fact, right from the first time the theorem was, that I was able to show the proof, I conjectured that actually finding the x here would be hard in some sense of hardness. And it seemed like a natural thing to give a hardness result. And I conjectured that from, I would say, 1985 plus epsilon until 2010 minus epsilon, when Bansal proved me wrong. And so the anecdote is that I used to think that, you know, you get to a certain age and, you know, what can you expect? Well, I thought, well, the best I can hope for is that one of my conjectures would be proven. But I was wrong. And so I'll say to you that it's even better when one of my conjectures is disproven. And that's what happened here. So I think this is a good time to take a break. We're good. That sounds good. We can stretch out. Let's see. So here's a combinatorial problem that I'll give to those of you that might speak here, which I try to do because I've got a similar, not so nice blackboard in my classroom, and that is to give a talk where you use each blackboard exactly once. It's a very tricky problem. It's even tricky. Here you have separate parts, but in my classroom the blackboards fold over the other ones, and so it makes it a very difficult combinatorial problem. All right. I think I'm going to skip I'm going to go to part 3, because just and leave out the wonderful results of Moser and with Tardosh. And I want to. So this is completely recent. In fact, I think it was Sumek just submitted it to Siam Discrete Math. And so the problem is to enumerate C of nk, which is...
This board, even though you want to use every board once, this one is not moving, right? So you cannot keep it visible.
I didn't say that everything will be visible forever.
I know.
Yeah, I know. Well, I didn't say I'd be successful either. Yeah. Let's see, can this go underneath? I'd have to be, that one's not moving? I don't think that. Let's see, if I move this one. Oh, this is good. I can at least go somewhat higher. So C of nk, we're talking about labeled graphs, n vertices, n minus 1 plus k edges, and connected. So the classic case is k equals 0, which is trees. And you too might know somebody that solved the k equals 1 problem. Many people did, but one of them, you may remember, was Alfred Rainey. He actually wrote a paper on counting unicyclic graphs. Very nice. And the general case for k fixed was given by E.M. Wright. And then the general case for all k and n was given by Bender, Canfield, and McKay in 1990. And it used there were some difference equations and then a very tight, careful looking at the errors, and they approximated it by differential equations. And they found the solution. But since then, there have been many, many other solutions. Now, once k gets bigger than n log n, most graphs are connected, so it's just the binomial coefficient. So the hard range is when k is small. And the particular range for Sumic is when k is smaller than square root of n. Actually, in his argument, he gives it square root of n over polylog n, but he told me that he could have handled that by some technical things.
You want to approximate this number.
You want an asymptotic formula, yeah. So you want, with the constant, you want an asymptotic formula for C of nk where k is in this range. And he'll actually include the case where k is a constant, okay? And the interesting thing is that the connection is to Brownian excursions. Okay, so what I'm going to do is I'm going to, given a graph G, and I'll label the vertices 0 through n minus 1, which will be convenient. And given a graph G that's connected, I'll create the breadth first search tree. Actually, I could use other things, but I just want it to be specific. I could have used depth first search. And also, just for specificity, in breadth first search, when a point is adjacent to a bunch of other points, you put them in a numerical order. Now, this is not necessary, but I just want to, so that given a graph, you create the breadth first search tree T, and since the graph is connected, it's going to be successful. So here's I've got all this colored chalk, so I might be able to. Yeah, and I'm always going to start at 0. Yeah. Since it's connected, it's got to work wherever you. But so I'm specifying 0. So let's say here's a breadth first search finds 1, 2, and 4, and then 1 finds nothing. Let's say that n equals 6 here. So 0 finds 1, 2, 4. Then 1 finds nothing, then 2 finds 5, then 4 finds nothing, and then 5 finds 3. And then if you like, 3 finds nothing. And so you get this breadth first search on a graph. And now we're going to describe this with the balls in bins. I'm going to make n bins, and actually the last bin is always going to be empty, but it's sort of convenient to write it this way. And the balls are going to be all the vertices except for the root. And I put the ball in the bin, which is the time at which the point is discovered. Where I have to define time, I mean, this time 1 is when vertex 0 is popped. And then so at time 1, 1, 2, and 4 are found. And then at time 2, nothing is found. At time 3, 5 is found. At time 4, nothing is found. At time 5, 3 is found. So, and furthermore, let's define z sub t equal the number of balls in bin T. And furthermore, we're going to look at the size of the Q when we apply this algorithm. So the Q starts out with 1. So what is the Q? It starts out at 0. Then we always pop the top of the Q. It becomes 1, 2, 4. Then we pop it. It becomes 2, 4. Then we pop 2 and find 5. Then we pop 4 and find nothing. Then we pop 5 and find 3. And then the Q becomes empty at this point. So we look at the Q size. The z's determine the Q size. The Q starts at 1. And at each point at time t, you add z sub t points to the Q, but you delete 1. So what happens is that the Q at time t is simply, so Q0 is 1, and the Q at time t, so I'll use Q for Q, convenient. So we're going to have a step size, which is zt minus 1. Now, if we look at the fact that there are exactly n minus 1 balls, that means that the sum of the z's is n minus 1, and it means that q sub n is going to be 0. So if we take the condition, so let's call it the bridge condition, is that q sub n is 0. So here the q function, it starts at 1 and it goes to 3 to 2 to 2 to 1 to 1 to 0. It's like a discrete walk, but we're going to approximate it by a continuous walk in a while. That's going to be the asymptotics. So the bridge condition is that we have that q sub n has to be 0 because we have precisely n minus 1 balls. Now, if you just are throwing n minus 1 balls into n bins, what is the distribution of the numbers z sub t? It's Poisson. It's Poisson. It's really sort of a surprising result if you haven't seen it before. If you let zt be Poisson 1 and let it be II, this is an exact result. Let zt be IID Poisson 1, and then look at the distribution given the fact of bridge, that is that the sum is, bridge is that here, it's that the sum is exactly t minus 1. That's exactly what you get. Just look at the numbers. It's exactly what you get The probability of getting values A1 through AT. You got all these factorials, and you got the factorials with the Poisson. And this is precisely the thing. If you haven't seen it before, I shouldn't show, you should check it yourself. It's just,
Well, what's the statement?
the statement is, it has nothing to do with the rest, except it's critical, but it's an independent thing. I take IID Poisson 1 distribution and take T of them, and then condition on the fact that their sum is T minus 1. So that's a distribution over Z1 through ZT. On the other hand, throw, sorry, this is up to Zn, I should say. On the other hand, take n minus 1 balls and throw them into n bins, and let y1 through yn be how many balls are in each bin. They're exactly the same distribution. The one distribution is can be given by multinomial coefficients. The other is given by products of Poissons, but the Poissons have this factorial in the bottom, comes out exactly the same. So this is just a wonderful fact. So to talk about the distribution contingent on bridge is to let the z's be Poisson 1 IID, but condition on bridge.
Yeah, but you didn't relate it to the graph or the distribution on this graph at all yet, right?
Right, yeah, not yet. In fact, the graph really hasn't appeared. This is more like talking about a random tree for the moment, yeah. In fact, the graph is only going to come in later. Okay.
But even here, the sum of any prefixes of the ZT should be...
Sorry.
The sum of any prefixes of the ZT?
Yes. So now the other condition, not all, that's right. So now, the condition excursion is that bridge holds, and also, as you said, the sum of any prefixes, it's a parking function. But the way I like to think about it is that the q's don't hit 0, except at the end. So if you look at a throwing of balls into the bins, first of all, you have to have exactly n minus 1 balls, okay? But then, will there be a tree that gives us the necessary and sufficient condition is that the Q doesn't, what I call early abort, that the Q doesn't reach 0. If the Q ever reaches 0, you can't have all the balls in the second bin, because then the root wouldn't have found anything. It would have been early abort. And this is necessary and sufficient. So this is actually a way of looking at trees. If you want to look at a tree, a random tree on n vertices, first, if you want a particular labeled random tree, you throw the n minus 1 balls into the nth bin, into the n bins. And by the way, excursion implies that this must be empty. So this is just, technically, I just want to keep this bin even though it has to be empty. And then you condition it on excursion, and then you will get a tree. The fact that the Q never reaches 0 is necessary and sufficient for getting a tree. And given a tree, there's a way to place the balls. And given the balls, since we were specific, given the balls satisfying excursion, there's a unique tree. So actually, before we get to counting graphs, this is a way of looking at a random tree. Throw down n balls, n minus 1 balls into the n bins, condition on excursion, and then that gives you, each tree is unique. So that gives you any of the n to the n minus 2 trees equally likely. So that by itself is very, very nice. Okay, now to get to the graphs. Okay, but it's a good place to, something you were, is that okay? Yeah. All right. Now the thing is,
It's not so clear how you would implement the condition. I mean, if you want to.
yeah, this won't be algorithmic. This is going to be enumerative. Yeah, yeah. That's right. That's right. Yeah, I mean, there are lots of problems. They're much. If you want to generate a random tree, there are much better ways to do it than this. Much better ways. Yeah, yeah. I mean, they're the. Can you? Well, I'm
Like a dynamic programming.
Oh, yeah.
Because you only have your current value of Q and your current number of balls left.
And then you get a distribution on the next number. Yeah. But given that these, what is that? The sequences. I'm forgetting that. I mean, there are lots of much. If that's all you want to do, this is not suggested as the way to. Proof. That's what proof for code. Yeah. I mean, proof for code is just is the way. I gave proof for code at Fazakosh a couple of years ago. Big success. Yeah. At least I had a good time. All right. Now, so a random tree connects to take independent Poisson ones and then condition on excursion. And that will give you a random tree. Now, given a graph, we map it into its breadth first search tree. Now we want to go backwards. Given the tree, what edges can we add back in so that the breadth first search tree stays the same? Now, let's look at this example. The graph couldn't have the vertex, the edge 0, 3, because then 0 would have discovered 3, which it didn't. It can't have 0, 5, but it could have 1, 2. Suppose in the graph 1 and 2 were adjacent. The breadth first search algorithm would not detect that because when you're doing breadth first search, you're always looking for new vertices. New vertices, so you wouldn't detect it. Similarly, 1 would not detect 2, 1 would not detect 4, 2 would not detect 4, and 4 would not detect 5. Right.
So if a node was found while you're in the queue, then you can add the edge.
Exactly. So if you have a pair of vertices, one of them is popped earlier than the other, because they're popped is the computer science term that it's for taking it off the top of the queue. So one of them is popped before the other, and the necessary and sufficient condition is exactly as Russell said, that what has to happen is that when the first one is popped, the second one is in the queue at that time. And then that would be okay. That edge could be added to the graph, and you'd still get the same breadth first search tree.
I think you mean pushed rather than popped.
Okay, I'm only half-time in computer science. Okay, is that pushed or?
Pushed is added, popped is deleted.
No, when it's
I want to take the top vertex and delete it from the queue.
popped, I think.
But so like 5 was pushed when 2 was popped.
Yeah, well, that's what I mean. Yeah, the first one was, 2 is popped and 5 is pushed, yeah.
When you pop, you check all the neighbors and you want to get
Right.
that when you check neighbors,
Yeah.
it's already in there.
Yeah. So it depends on whether you want to look at the first vertex or the second vertex. I want to look at the first vertex, and that's the one that's popped. Okay. All right. So how many of these blue edges are there? Given the tree, how many blue edges are there? Well, it's the number of pairs where at some time Like if you look at 1, 4, at some time 1 was popped and 4 was already in the queue. So 1 was at the top of the queue and 4 was in the queue. So it's the sum over all vertices. Every vertex is popped at some point. It's the sum over all vertices of, at the time that vertex is popped, the size of the queue minus 1. And the thing is, the sum over all vertices is the sum over all time, because every vertex gets popped. So the result is, all of this is still precise. You look at the queue sizes, and at each time you look at the queue size minus 1, and that gives you those blue edges, and each blue edge is there exactly once. But since you're summing over each vertex being the first vertex, change it to the sum over time. So what happens is, what can G be? We haven't even, we're about to get to the number of edges, but just which G have the property that they give a given breadth, that they have a given breadth first search tree T? Well, you have, of course you have T because G contains T, and then you've got these M other edges, and you can take any subset of them, and exactly any subset of it. So if you just want to count graphs with a given breadth first search tree, it's just, actually that count would be 2 to the M. You could add any of them. Now what we want to do, so we're about to get to an exact theorem. So therefore, the number of G, and let me just, now I'm specifying the number of vertices and the number of edges, such that the breadth first search tree of G is T, is exactly M choose K. M choose K, because you've got these M potential, you've got these M blue edges, and you can take any K of them. But that's all you can do. That's exactly what you can do. It's so this is still exact. This is still exact. Yeah. Is that okay? Here I'm specifying that the number of edges is precisely n minus 1 plus k. It's the first time I've done it. So now I'm saying they'll be exactly k. So this might be 0. This might be 0. It could well be. I mean, if the breadth first search tree, for example, is a line, if 0 finds 1, which finds 2, which finds 3, which finds 4, up to finds n, you can't have any other edge there. That's the only, then m is 0. On the other extreme, if 0 is adjacent to everything, then you could add on any number of other edges and you'd still get the graph. Okay, but this is the exact result, and therefore C of nk is the sum over all trees on n vertices of M choose K. Yeah, M depends on the tree. And I should put it here, if you like. Okay. Which is, but what is the distribution of M M is a function of the Q's. The Q's are a function of the Z's. The Z's are Poisson 1 IID, and then we condition on excursion. And so times n to the n minus 2 Okay, what do I want to say here? This sum is just the expected value, is n to the n minus 2 times the expected value of this given a random tree. But a random tree is just take the z's as Poisson 1 and condition on it being on excursion. And so this is still an exact result. The C of nk is precisely, no approximations yet, we're about to come to them. C of nk is precisely n to the n minus 2 times the expected value of this, where now the distribution, forget about trees, the distribution is that the z's are Poisson 1, and we're conditioning on excursion, and then we define m this way. So, what does this look like? Well, here's the Q graph, and the discrete walk is that we start at 1 and we end at 0, and each step is Poisson 1 minus 1. And we condition on the fact that this walk, so I'm drawing it in a more continuous way, that this walk is an excursion, Now what does this look like? It looks like Brownian excursion. Now it's discrete, but it looks like Brownian excursion. You're starting at 1 instead of 0. And what is the scaling? Let's scale this by n in the scaling. So make it from 0 to 1. And then the natural scaling here is by square root of n. And so this just becomes a continuous picture. Well, actually, I drew it as a continuous picture, so it doesn't look very much different, but okay. So if you accept that, then what is the expected value of m choose k? There's a 1 over k factorial. The scaling is going to, and now the m lower k turns out to be m to the k. All these things have to be proven, but if you look at the rough size of m, at least in this range, it's such that m lower k and m to the k are pretty close. So it's like m to the k, but m, I like to put double squiggle, meaning that has no formal definition. It means m is sort of like, I don't mean, so now I'm in the land of approximation. M is sort of like, now, oh, and what is m? M is the area. M is the area. It's the area under this curve. Except that we've scaled by n and n to the 1/2, so it's n to the 3/2 times the area. So m is like n to the 3/2 times, let me call it the scaled version, which is just you scale. It's like n to the 3/2, to the k, n to the 3k over 2. So no, this is right, n to the 3/2. So m is looking like n to the 3/2, which is the scaling, times, now you have a Brownian excursion, and m is the area under the Brownian excursion, something that has been studied quite a bit. Now, so what you would then like to have, given this, is that this is going to be like n to the 3k over 2, because the m lower k, it's like m to the k. That's not so hard, the technical part. You just bound it from below by m minus k to the k. That part looks hard, but it's not. And then what you have is the kth moment of the Brownian excursion. And in fact, this gives the right constants, and this was known some time ago. That is, so what E.M. Wright showed was that C of nk is, for fixed k, is n to the n minus 2 times n to the 3k over 2. Each additional edge gives a factor of n to the 3 halves. Very non-obvious fact, but that comes out of this. And then furthermore times a constant, and Wright found the constants in a different way, looking at some things, but then it was seen that those constants are the moments of this classical problem, the area under a Brownian excursion.
But what about the condition? Is that if a Brownian excursion model of this condition, right?
Those conditions are excursion. You see, this condition is that you end up at 0, and this condition is that you stay above 0. So it's exactly, well, exactly, but one's discrete and the other's continuous. Now, one of the questions here, the question when I spoke to Sumik about this, is that this is all well and good, and for k fixed, it's one thing, but what if k is going to infinity? Oh, and sorry, and why is it Brownian excursion? Sorry, I left out a crucial thing.
You didn't really define Brownian.
Yeah, I don't want to do that, but let me say why it's Brownian excursion without defining it. So, if you look at a single step in the discrete walk, it's Poisson 1 minus 1. And the thing about Poisson 1 minus 1 is it has 0 drift, and its variance is 1. So if you just look at its mu and its sigma squared, it's like flipping a coin. And a Brownian walk is as if you just flipped coins and looked at the sum. And now you condition on the fact that you end up back at 0. And a Brownian excursion is, it's an infinite object, so it's over these infinite paths. So defining it is not so easy. But as a discrete thing, think of just flipping coins and looking at the walk, but condition on the fact that you return to 0 at time n and that you've stayed above 0. And then go to the limit and scale it appropriately, and you'll get a thing over the curves. And that's what's called Brownian excursion.
So it's just the limit of this discrete
It's-
coin toss in process.
Yeah, but there's some people in probability that would say this discrete thing is just a discretization of the real thing. So
Don't they call it Brownian bridge?
I'm always confused about which. One is that you end up at 0, and the other is that you end up at 0 and stay above 0.
First time it hits 0. So
All right, I'll have to, sorry. Yeah, is that right? I always get confused between these two things. So let me say
As long as you're consistent.
all right. What I'm saying is I'm requiring that it hits 0 at time n for the first time. It does hit 0 at time n and for the first time. So the step size, each small step size has mean 0 and variance 1. Now the notion then is that in the limit, it doesn't really matter which distribution you have, whether it was just equally likely plus 1 or minus 1, or whether it was Poisson 1 minus 1. You can make the calculation. Poisson 1 minus 1 has mean 0 and variance 1. And sort of the sense is that if that's the step, when you look at the large picture, it's going to look the same. And then there are other points, which is, this is discrete, and also it starts at 1 instead of 0, so you'd like to say these are negligible. But it turns out the real problem is you're looking at ultra-high moments. You're looking at ultra-high moments. So what happens when k approaches infinity? And so the question I talked to Sumik about, and we knew the answer because of the results of Bender, Canfield, and McKay, because, see, this is an equality, so we actually know what the final answer is going to be. For how long, if you want to look at this approximation by the kth moment of m, and suppose k is going to infinity with n, for how long does this approximation of this discrete thing by this quantity, for how long does it hold up? I mean, if n is fixed and then k was much, much larger than n, it wouldn't hold up at all because for n fixed, in the actual excursion, there's a maximum place you reach. So you're, and yet in the Brownian excursion, you might go above that, and if you take a super ultra high moment, those would come into play. So for how long does it go up? And Sumik, this turned out to be exactly stuff that he looks at, which is to take continuous things like a Brownian excursion and say, you have something that's supposed to approximate it with a discrete thing that's supposed to approximate it. How well does it approximate it? Or does it? Here the question is, how high a moment can you have where the moment depends on n so that this approximation is valid? And what he was able to show was that as long as k grows slower than root n, that this approximation of the discrete walk by the Brownian excursion is accurate for this ultra-high moment. Whereas if you take the moment to, once the moment gets up to square root of k, square root of n, new things come in, and it's no longer right. And we knew that was the answer because we knew all the answers before, but what he has done is he's really found a new proof, and to me a very insightful proof, for finding C of nk as long as k and it goes up to root n. Of course, there are other regions and other work has to be done, but that's what he did. So
can you explain why root n and what goes into a proof that's up to this?
you'll have to invite Sumik to give a talk. Yeah, I couldn't see it. Looking at it, I couldn't see what was going on at square root of n.
Well, what is the type of proof that tells you that you are fine up to that? Or up to
It's a sophisticated, yeah. Unfortunately, while I can talk about his result, I can't talk about the way he proved it, because this used some real probabilistic things about how you approximate discrete things by, when you approximate discrete things by continuous things, what are the errors? So here, the other one I was able to give the proof. Here I'm able to get right up to the proof, but sorry, I have to leave it to Sumik to explain what the proof is. And the crucial question, why square root of n? What is the nature of the barrier when you reach square root of n? Which I mean, I can see some barriers are coming in. As the moment gets higher and higher, you have a discrete walk. You're approximating a continuous walk by a discrete walk. If the moment gets super high, you're just looking at the max. And
so nevertheless, they are able in the previous proof to get to n log n, which is above n.
oh, they did, okay, but they didn't use this method at all. They used completely different methods.
But the answer is,
Yeah, so no, they were using a completely different methodology. So just to say a few words of the history, and then maybe that's enough for today, is that C of nk actually has a long history. After Bender, Canfield, and McKay, there were several other people that had different approaches. I have a paper with Remco van der Hofstad. There are results that involve the giant component. There's by Matthias, I forget exactly who. So there have been a number of people that have looked at it, and but this approach, at least for this range, I find particularly compelling. But you're right, I'd like to know it for, what's going on at square root of n. Can one give a good explanation, a good probabilistic explanation? Is it the fact that the walk is Poisson 1 minus 1, and so the third moments are coming in, or I don't know what it is. I mean, see, if all the steps were Gaussian 1, then you'd be a lot closer. You'd be closer to. But I'm sorry, I don't know the answer. Good question. But I decided I'm not going to do the 2 hours. I'm going to do 2 out of 3. So yeah.
Thanks.
Okay. Thank you.